Welcome everyone. So this is our 69th live stream geometry. We have 3 people here with us so far. And today I'm going to do 2 problems from the Vietnam team selection test in 2022, which I think finished recently. And then the other 4 problems I chose from the Math Olympiad Summer Program in the US. So there's a certain program for students in the US who are training to make the IMO, and there's like 3 levels. Black is the hardest level, and I chose problems from that level in 2005. So it's the hardest level, but it was a long time ago, so maybe it'll be a little bit easier than what it would be today. So with that, I will start sharing my screen. Hold on just a second. Sorry, give me 1 second. All right, so here is the first problem. So Vietnam's questions are often 2 parts. So this one is also a 2-part question. We have a triangle ABC and a circle with center O. So let's draw that. I see someone posted something in the chat. Check. Okay, this is problem 4. So this is the easiest of the second day. And then there was another problem I did that was like the hardest of the first day. Okay. So O is going to be the center of this circle. And then there's a line through O and the midpoint of BC. So we call the midpoint of BC I. And this is going to be the perpendicular bisector of BC. We want to see where it intersects AB and AC. Okay, so we'll have to make a little more room here. We'll have to extend AB. And let me see if I can change this diagram so we have more room. Maybe something like that, but I don't want O and I to be so close together. So how should I draw this? Let me shrink it just a little bit. Okay. I think that's good enough. Okay, so basically, let me move it to the right just a little bit so that it, there we go. Okay, so E and F. So E is where it meets AB, and F is where it meets AC. D and G are the reflections of A over O and the circumcenter of AEF. So let's draw this circle. And then let's draw the circumcenter. Okay, so the antipode of A in those 2, let's rename this as, I don't know, I'll call it R. So basically we draw the 2 antipodes of A in those 2 circles. This one is going to be D. So AD is a diameter and AG is a diameter. And K is the reflection of O over the circumcenter of OBC. So kind of a lot of stuff here. Okay, now we're gonna have to make more room. So try to make this like a smaller figure. We want to see the circumcenter of BOC basically. Yeah, maybe, you know what? Let me do this. See if this gives me a little more room. Yes. Okay. So I kind of like this diagram here. We want the center of the circle BOC. So I'm going to draw that. Let's call it S. And we want the reflection of O over S. So basically we have another diameter. So this would be K. This is interesting. So we want to, first we want to show that DG and K are collinear. All right, let me make this look a little nicer. So you have this one big line going through all three circles. And AG is the diameter, AD is the diameter, and OK is the diameter. And we want to show that those are collinear. All right. Is this 90 degrees? I think it might be. Let's play around with it and check. Yeah, this looks like a right angle. It's probably not hard to prove. Yeah, because this is 180 degrees in total. Let's see. This angle is going to be half of this arc. This angle is half of this arc. So what if we did a homothety with factor 1/2? That would mean if we take the midpoint of AK, then we want to show that RO and that point are collinear. So yeah, can we show that RO and J are collinear? That would be another way to do it. So RO is the line between the two centers. We can show that DG passes through the intersection of R and O. Okay, yeah, and that would also solve it. That's a good point. Well, no, that wouldn't solve it. That's just something that we know. We know those three are collinear.
And maybe from that, we need to prove that LB passes through K.
Yeah.
Which means, well, we need to prove that LBDC is a harmonic quadrilateral.
Okay. Sorry, did you say LBKC?
LBDC. If we can prove that it is harmonic, then we know K is the intersection of the two tangents.
Yeah.
So if it is harmonic, then it must pass through K.
All right, that makes sense. So if we can show that LBDC is harmonic, that would solve the problem. or for part A. It's a good point. So what can we project through? Maybe we can project through A. Oh, what is H? No. Oh yeah, we should get rid of H here. All right. So let's try to find the best way to show that LBBC is harmonic. What if we projected those 4 points through A onto this circle? Can we do that? I think we can do that. So it would be E, L, F. Oh, is AB tangent to the circle?
Yeah, it is. I can prove that by using languages, easy languages.
Okay. So then we want to show EAFL is harmonic. Is that true? Yeah, I'm not sure. I think we can do that. Like project through A onto this circle. So if we draw the tangents at E and F, does AL pass through that? Yes.
Actually, EF passes through the tangent at A and L, so it must be harmonic.
Ah, so that solves the problem.
Yeah.
All right, so we've solved part A. So I'll write it up. Okay, so the tangent, so for part A, the tangents to the circle BOC at B and C pass through K. And then we also, by a homophily at A with factor 2, so I'll say let R be the center of AEF. So OR passes through the midpoint of AL, so GL and D are collinear. I'll just say OR bisects AL, and that means that G, L and D are collinear. Okay. And then we want to show LBCD is harmonic, but so we can project through A. So Oh, but first we want to show that AD is tangent to this circle, right? You said we can do that using inversion.
Maybe just angle chase.
Yeah, it should just be angle chase. Yeah, because angle DAC, we want to show it's equal to angle AEF, which is 180 minus A, then minus this, which is 90 minus C. So first I'll say angle AEF. That's 180 minus angle A minus minus this angle, which is 90 minus angle C. And if you simplify that, that should be this angle, which is basically, so that would be 90 minus B. And that's angle DAC. All right. So AD is tangent to the circle AEF. So then projecting through A, onto that circle, we then have LBBC is equal to LEAG and LEAG is harmonic because the tangents at A and L, or I'm sorry, LEAF. Where did I say G? Yeah. So the tangents to AEF at what are the 2 points A and L? And EF concur at point O. And that means that LEAF is harmonic, which implies LBDC is harmonic. So LD passes through K, and so DG and K are collinear. That's a nice one. All right, so that is part A. And now for part B. So let's draw that segment in. Now we want to let M and N be points on KB and KC. Looks like Anmol just joined. Hey Anmol, so we just got through part A of this question from the Vietnam team selection test. And now we're going to work through part B. So let M and N be points on KB and KC so that IM is perpendicular to AC. And IN is perpendicular to AB. It's kind of interesting. So this, I'll draw, okay, so this is M, and this is N, and I'll draw these two perpendiculars, P and Q. Then we draw the perpendicular bisector of IK, and we see where it meets MN. Oops. Let me make this look nicer. All right. Do that. Pick that. Let's draw the perpendicular bisector of OK. Or I'm sorry, IK. So we have the perpendicular bisector IK. Might as well draw this point right here. And it meets MN at H. Interesting. So that's point H right there. Okay. Assume that IH, wow, this is very complicated. IH intersects AB and AC at P and Q. Oh, I just made these P and Q, so I got to change them. I'll call it X and Y. I'll call this X, and I'll call this Y. This is, I feel like this diagram is just too complicated. Let's see. But a lot of the rest of the figure we don't use anymore, so maybe it's not so bad. So it intersects IH, intersects AB at P, and AC at Q. We want to show the circumcircle of APQ intersects O for the second time at a point on AI. All right, let me clean this up. So we have MN and TH. Yeah, it's kind of problems like these why I like using GeoGebra, although I know it's not allowed on the actual test. Let's move this a little bit to the right. I want to move the figure, but not the text, but I can't do that. So I'll just move all these one by one. Okay, so let's draw the circumcircle of APQ. And we probably don't need a lot of the rest of the figure. So we want to see where it intersects this circle. So, and we want to show that AI is collinear with this point. We call it U. So should I try erasing everything I don't need? That might be helpful. The only thing I need here, there's a lot of stuff I don't need anymore, right? So I'm going to hide it all. I don't think we need that. We need X and Y. That might be everything I can delete, actually. Yeah. Okay, so I'll draw this then. What was S? I'm gonna go hide that. I think this, maybe AK I can get rid of. And J. And I think that's everything. All right. So we define M and N, and then we let MN intersect that perpendicular bisector by K. And then we draw IH. There's a lot going on here still. So we want to show AU is like a median of ABC. But we know AK is a symmedian. I don't know if that helps. And looks like we have someone else, Coffee. I think he'll join in just a second. Hi, Coffee. Thanks for joining. So yeah, AK is a symmedian, and we want to show AU is a median. This is kind of tricky. So yeah, maybe I should draw AK back in. And I wonder if these concur. So yeah, this is where GeoGebra gives some stuff away, but no, they don't concur. But yeah, I feel like, yeah, this is a or to me, it seems like this is a complicated figure. We know AYIX is cyclic. Not sure if that helps. How do we use that HT as a perpendicular bisector? Yeah, this feels like just so much information. I don't know if we could use the isogonal line lemma. So we want to show AK and AU are isogonal. Well, we could try to show that I lies on the radical axis of these two circles. That's probably an easier way to think about it, right? So we know the power of I with respect to this circle is basically BC squared over 4. And then for the power of I with respect to this other circle, how can we compute it? Let me see if we can find the center of that circle. Is there anything special about that? It almost looks like AV is perpendicular to BC, although I'm not sure if that's true. We just need to prove PQ is perpendicular to AB. Let me think about that. How did you get that?
So we need to prove that A, I, and U are collinear. Which means we need to prove that I lies on the radical axis of APQ and circle O. So it is the same as showing IB times IC equals IP times IQ.
Yes.
So which means it is the same as saying that PQ is the anti-parallel line with respect to BC.
Okay.
So we need to prove PQ is perpendicular to AD.
Ah, interesting. That's a good observation. All right, so we want to show PQ is perpendicular to AD. Or IH is perpendicular to AB. That's another way to say it. All right. Okay, so we want to show IH is perpendicular to AB. What else can we use with that? We know TH is perpendicular to OT. So I think it's kind of like saying angle IHT, we want to show as angle IOD. I think that would solve it. Maybe actually, let's see. Yeah, I think that's right. Can we say anything about this circle? It looks like O, U, T, H, and this point are cyclic. So U lies on that circle. So yeah, is that obvious? So angle OUH is 90 degrees. So HU basically is tangent to this circle. I'm not sure why, but that's what it looks like. But yeah, I'm not sure if that makes the problem easier actually, or if that's just the same thing. Let's see. We could also, I wonder if we can use the radical axis theorem. So what if we dropped a perpendicular from I to AB? And we try to show that that point I and H are collinear. Could we use the radical axis theorem somehow? Because then we would know that all AI, AYI, this point in X are cyclic. And would we have any other cyclic quadrilaterals? Let's see, what if I label this point right here? IV. This is kind of interesting. Is HU and D collinear? Well, I thought HU is tangent, so I wouldn't think it would be collinear now. All right, I'll spend a couple more minutes on this, maybe 5 more minutes, and then we could try moving on to the next one. I think we're close. So we have to use M and N somewhere. We want to show IH is perpendicular AD. I'm not sure how good the radical axis theorem will be. Is there some circle passing through M and N that we could use? Maybe M. Yeah, I don't see any nice circle through M and N. So probably not. How can we use points M and N? I don't know if we could use Desargues' theorem. So we want to show, we want to show, we could define V as the perpendicular. And then we want to show IV, MN, and this perpendicular bisector are concurrent. That's another way to do it. So we want to show IV meets MN on the perpendicular bisector of IK. I don't know if it would help to reflect I over H, so we get a point over here, and then this would be tangent to the circle. Just throwing out ideas.
I think I've come up with a solution, and it's quite complicated.
Okay.
So my idea is we need to delete a couple points and turn this into an easier problem.
Okay.
So can you draw the tangent at A of the circle O?
Okay.
And can you let it meet KB and KC at 2 points?
Yes. All right.
So my idea is that instead of working with triangle ABC, we will be working with triangle KWZ. So consider triangle KW and Z. We have O is the in center, and we have we have B and C are the tangent points.
Okay.
And I is the midpoint. So I'm gonna delete a couple points.
Okay.
And,
so we're gonna work with KWZ.
Yeah.
And I is the in center, you said?
Yeah.
Is that?
O is the in center. O is the in
center. Oh,
center.
sorry. O is the in center. Okay. All right.
So next I'm gonna let IN meet KB at a point.
IN meets KD.
KB.
Okay. Sorry, I think you said KB, right?
KB.
Okay. KV.
No, KW, KB or KW, they are the same.
Okay. All right, KB. Sorry about that. Okay.
And similarly, we let IM meet KZ at a point.
All right.
So I draw these points so that I can use the fact that can you connect OW?
Okay. Hold on just a second. OW?
Yeah, OW.
Are you want me to draw the whole line?
No, the segment.
Okay. All right.
So I'm going to use the point A1 now. So we have IA1 and OW are parallel because they are perpendicular to AB.
Okay.
So
That makes sense.
so we have KA1 over KW is equals to KI over KO, which is equal to KB1 over KZ. So we
Okay.
have A1, B1 must be parallel to WZ.
All right.
Can you connect it? Yeah. So we consider the two triangle KA1, B1 and triangle KWZ.
Okay.
We can see that WO is parallel to A1I and B1I is parallel to ZO.
Okay.
And since O is the in-center of triangle KWZ, then I must be the in-center of KA1B1.
Okay, let me think about that. So you're using a homothency.
Yeah.
Parallel, yeah, I see what you're saying. Yeah. So I has to be the in center of KA1B1.
Yeah, so that's how I use the point M and N. Maybe now we can consider in triangle KA1B1. We have I is the in-center. We have A1N and B1M are the angle bisector. So the problem turns out to be a lot easier. We can delete a lot of points.
Okay.
So I'm gonna redefine the problem. So given triangle KA1B1, A1N and B1M are the angle bisector, and MN meets the perpendicular bisector of IK at a point H, and we need to prove that IH is parallel to A1B1.
Okay. And in order to have point K, we still need point O, right? Oh no, because you just draw the tangents to, well.
So let me write it in the chat for you.
Okay. But yeah, I see what you're saying. We have triangle KA1B1 and I is the in-center and M and N are the theta angle bisectors. And then MN, but yeah, we still need point K, I think, right?
Yeah, so basically we just need to keep point K, point A1, B1, MN, I, H, T. That's it. We just need to keep those. We can just delete A, B, C, and stop.
Okay. Do you want me to actually delete it, hide it here?
Yeah,
or just
if you feel that it's more comfortable, then we should hide it.
Okay. Okay. Let me see what that looks like so far. So we have triangle KA1B1. Let me hide some of the other stuff here. Okay, so KA1B1, I is the in-center. And then, M and N are the feet of the angle bisectors. So I should show that. We want to show that IH is parallel to A1B1. We don't need that. We don't need that. That. So the only thing is, how do you define B and C? And like, do we need point A or?
Actually, we don't even need A, B, and C. Like, we just need to prove that this fact, and then we just apply it into the original configuration. Then we're done.
So how do you define point K?
Like, no, this is, I'm just like, I'm just, redefining this as a lemma. And if we can prove this lemma, then we just need to apply it into the original problem.
Okay, so, okay, because you said, oh, I think I see, I get it. So yeah, we don't need this circle anymore. And we don't need this. Okay. Yeah, I see what you're saying. So it's just like this.
Yeah, this is a lemma. We prove this lemma, and then we apply into the problem, and then we have like the two perpendicular line that I say originally, and then we prove the claim.
Okay. So I'll start writing this up. So yeah, let me think about this. Is this obvious to prove? It's probably not that hard, I agree. Let's think.
Oh, I think this is a lemma that I've met before. Let me check. I think I wrote it down in my book. Yeah, let me just check it for 1 second.
Okay.
Because I worked with in-centers a lot, so I think I've seen this lemma before.
Okay.
Oh, okay. So, can you draw the circumcircle of KA1B1?
Okay.
So, they give us the perpendicular bisector of IK. So it reminds me of when you let B1M meet the circle at a point, and you let A1N meet the circle at another point, then the line connecting those 2 points is the perpendicular bisector.
Okay, yeah, I see what you're saying. So
yeah, this is the what's in-center extender lemma, I think.
not the in-center external, or there's a couple. Well, actually, yeah, you could think of it as like, yeah, the in-center external lemma. So yeah, basically you're saying that because yeah, basically C1I is C1K and D1I is D1K. Yeah, that's both by the in-center external lemma, and yes, then okay.
So, yeah, the perpendicular bisector just remind me of that, and then we need to prove that IH is parallel to D1.
Yeah. Feels a little like projective geometry to me, showing the parallel, but maybe there's another way to do it.
Maybe we could try that, but but I drew the points D1 and C1, so maybe we find way to use Pascal or something maybe.
Or let's see, what if we said, like, what if we look at these 4 points and we project it through I onto HC1? So, so if we take those 4 points and we project it onto A1B1, we want to show that that would be like ME1 over E1N. But if we project it onto this, yeah, I don't know, maybe I'm making it harder. Is HK tangent to the circle?
Yeah, that's right, that's right. We can prove that by using the degenerate version of Pascal.
That HK is tangent.
Yeah. That's a good observation. I think we use Pascal for the 5 points on the big circle.
Okay.
Yeah,
so,
because you know their intersections are the point H, M, and N, and those 3 intersections are collinear, so it must be the tangent.
Okay, interesting. So
and,
sorry, go ahead.
So we have, I think we can do an angle chase now because can you connect KI and A1B1? KI.
Yeah, I think it's an angle. I agree. It looks like an angle
Yeah.
chase at this point. Wow,
Yeah,
what a solution.
Yeah, it's a really hard.
All right. And so basically we just need to show angle AF1K is angle HIK, but HIK is the same as HKI. And KI we know is an angle bisector here. So HKI is HKG1. That's going to be half of arc A1B1. And this angle, angle AF1K, we could probably show by is half of this arc plus this arc. We want to show, I think we want to show arc A1K equals arc BG1. This is B1G1, is that? I don't think that's true. Let's see. But yeah, it should be an angle chase. Oh yeah, okay, I think I got it. So angle HKG1 is half of this whole arc, and angle angle A1F1K is half the sum of these arcs, but this arc is the same as this arc, so it's the same thing. So yeah, that proves it. All right, so we have solved it. Yeah, it's going to take a little while to write out, but yeah, this is a really cool solution. There's a lot of stuff in it. All right. So let's unhide everything. Well, not everything. Yeah, like I don't want to unhide that. Everything that we needed just for the second part of the problem. Whoops, I unhided too much. Like, for some reason, when you unhide too much, it like unhides everything. So let me do this one more time. B and C. All right, let's see how that looks for now. How does that look? All right, so let me bring back point A. Let's bring back that segment. We also want the okay. Okay, so yeah, I'm probably going to need to make more room here. Okay, so we want to show that Pbqc is cyclic. Yes. So I'll say if Pbqc is cyclic, which we're going to prove, then BC and QP are anti-parallel. And so, no, actually, if Pbqc is cyclic, then I is the radical center of those three circles. Okay, so what are the three circles? Pbqc and APQ. And that would mean APQ meets O on AI. Okay, so we're going to prove that Pbqc is cyclic. So and we have Pbqc is cyclic if and only if BQ, PQ, and BC are anti-parallel. Anti-parallel. And that's the same as saying that PQ is perpendicular to AB, which is the same as saying IH is perpendicular to AB. Okay, and then we want to let KB let KB and KC, so draw the tangent at A to ABC. let it meet KB and KC at W, Z. Okay, so now we're going to need more room for let's see. Let me see, maybe I have some room here. So I'll move everything over. Wow, so this is the easiest problem. There's a lot that went into this for the easiest problem.
Yeah, and if I had to know the lemma that I show you, then maybe it will take me like even
More
longer.
time.
Yeah. This is
So
like higher low level, so it's really hard.
Yeah, it's tricky. Let IN and IM let IN and IM meet KW and KZ at A1 and B1. We should be able to fit this stuff in. Oops. Then so then we have I is the in-center of, so O is the in-center of, I'll just say, yeah, I'm just going to shorten everything here. So O is the in-center of KWZ. And it's not hard to show that KA1B1. So we have KA1B1 is homothetic to KWZ. I'll just say show this. So we were able to prove this, but I'm just going to abbreviate. I'm just going to shorten everything for now. So that means that A1B1 is parallel to WZ. And WZ is perpendicular to AD. So this means that A1B1 is perpendicular to AD. Yeah, I'm not even going to write that now. So yeah, I'm just going to try to do this as fast as possible. So we drew the circle KA1B1. So let B1I and A1I meet the circle KA1B1. at D1 and E1. Or did I call it E1? Let's see, D1 and C1. D1 and C1. And I'll just say not hard to show HD1 and C1 are collinear. I'll just say HD1C1 is the perp bisector of IK. And then from there, yeah, I might as well just say by an angle chase. It's not hard to show. Oh, then we use Pascal's theorem. So by Pascal's theorem, I'm just going to let the YouTube viewers figure it out at this point. HK is tangent to AD1C1. Wow, what a solution. This is an amazing solution. So then by an angle chase, IH is parallel to A1B1. H is parallel to A1B1. And that implies IH is perpendicular to AB, which solves the problem. Implies, I'll just say which solves the problem. All right, I'm going to move on to the next one, but this is an amazing solution. So yeah, thanks for figuring it out. This is fun. All right, so we're almost halfway through the session. This problem is it's supposed to be even harder. Let's see how far we can get. So
I think we should try the other ones because this one is even harder than the previous one.
Okay, yeah, let's do the others.
I have only solved part A of it, and the part B is just too hard, I think. So maybe just leave it later.
Okay, I think this problem is a little easier, or this one should be easier. So yeah, this is from the US IMO training, but it's all the way back in 2005. So things weren't as hard back then, I don't think. Circle with center O is tangent to this. Okay, so really, here's how we do it. Draw a circle with center O. So let's call this O. And let's draw the tangents at B and C. Yeah, I think this problem is probably pretty easy. It's probably just like projective geometry. So this will be, but I think the next couple, I think, get a little harder. So let's see. Okay. So that's point A. And M is a point, M is any point here. And then EM and CM, we try to see where it intersects AO. Okay. The larger arc BC. Okay, so we want to draw the line AO. This looks like just a bunch of harmonic quadrilaterals, I think. Let's see. Okay, let's do it something like that. Okay, I'm going to draw this point because we could use that. We get a harmonic quadrilateral. So EM intersects it at P, and CM intersects it at Q. And K is the perpendicular from P to AC. And L is the perpendicular from Q to AB. Okay, so this is K. This is L. We want to show OM and KL are perpendicular. That's kind of interesting. Maybe it's just orthocenters even. Maybe you don't even need sorry. I'm going to read the comment in just a second. Let me just hide a bunch of stuff. It's just too many lines.
Can you make MBC an acute triangle? I think it will be nicer.
Okay. So PK is perpendicular to AC and QL. So you said BCM, make it an acute triangle, right?
Yeah.
Let's see. So let's see, hold on. I'll try to make this a little smaller. What happens if I try to make it acute? Oh, the way I drew this, yeah, I'm going to have to redraw some of it. Unless, I mean, I could move B and C more towards the bottom of the circle, but
never mind. Maybe we can just let it be like that.
So yeah, I could do it. Let's see. I just have to, CM would intersect the circle, like AO down here instead. I'll just leave it like this for now. So, okay. So we want to show OM and KL are perpendicular. So I guess one way we could try to do that, we show that KO squared minus LO squared. Well, that's probably not that good. Let me check the chat. It's similar to the previous one. Okay, bring O in the interior of BCM. Oh, that's what Anmal was. Okay, so Anmal was saying. Yeah, and you know what? I'm gonna do that. I'm just gonna redraw the figure. So we want to see where CM meets AO. Okay, so Does that work? Let's see. BM meets it at P and CM meets it at Q. K is the perpendicular from, yeah, and L is a perpendicular from Q to AB. We want to show OM and KL. Yeah, that looks good. Okay. Maybe something more like this. Yeah, I like that. So PK is perpendicular and QL is perpendicular. Let's see. Maybe this is a little harder than I thought. Yeah, it seems like it should be easy, but I don't know. Can we use orthocenters? Because we have a lot of right angles. How about we make a tangent at M to complete a triangle with an incircle? Okay. Yeah, I kind of like that. Waiting for this to disappear. There we go. So we have basically triangle ADF, and then we have the incircle of it. Good to see you, Jamin. Thanks for joining. So yeah, he just told me yes to hop off. All right. So OM is perpendicular to DF. And so we could try to show DF is parallel to KL. That's one way we could do this. And does this use like the Iran lemma? So I think, I don't know if ACDQ is cyclic. No, it's not. Isn't there something special about this point Q? Like, so it's where CM meets AO, or O is the end center. Is that the Iran lemma, or is that something different? Yeah, maybe we could calculate AK over KF an AL over LD. Or AK over AF. Maybe we could project.
I think we can do it like the same way as the previous problem. So you remember, like, it has a similar statement where AO meets MB and MC. So in the previous one, we drew the tangent at M. Oh yeah, you already did, right?
Yeah, so I drew that tangent.
Oh yeah, I wasn't noticing because I tapped out to do my own thing.
Oh, it's all right.
Yeah, so prove that KO and DF parallel, right?
Yeah, we want to show KL and DF are parallel. PQ and DF, so I'm going to do it and all S. So yeah, we want to find AK over KF, show that it's AL over LD. There's some kind of homothety. So we know AL over AB is AO over OQ, and we want to find AL over AD. So basically, wait, let's think about that. So AL over AB is AQ over AO, and AF or AK over AC is AP over AO. So the ratio of those two would be AP over AQ. So basically, I think we want to show that AD over AF is AQ over AP. Is that right? And I wonder if this is a right angle right here. It looks like it. If it is, that would solve the problem.
Which angle you say?
Angle APF.
I think it is like because of the Iran lemma.
Ah, so we're using the Iran lemma. Okay, so let me think about this. Yes, that's the Iran lemma. Okay, so I think we've solved the problem. Oh, I think Anmol thought of it a little differently. Since MD is the tangent, MB, MC, MA, and MD are harmonic. Ink to pencil. So yeah, I'm gonna write out like what I was thinking at first. So we have angle, so let the tangent at M meet A, B, and AC at D and F. And then by the Iran lemma, angle APF is 90 and angle AQD is 90. Is that, let's see. Because P lies on the angle bisector. So yeah, so so this means O is the end center of ADF. By the Iran lemma, angle APF is 90. And angle AQT is 90. So that means that APF is similar to AQD. Since AO is an angle bisector. And so, yeah, here we could just use a bunch of ratios. So AD over AQ is AF over AP. And then we also have what was the other ratio I had? Also AOB is similar to ALQ. So AOB is similar to ALQ. And triangle AOC is similar to APK. Okay. Yeah, right after this, I'll look at the proof you mentioned. So we have AO over AP is, sorry, AO over AQ is AB over AL. And we also have AO over AP is equal to AC over AK. And then combining all those, what happened here? AO, not sure what I did there. Must have just pressed the wrong buttons on the keyboard. So then combining the above, AL over AD, or AD over AL is AF over AK. And so KL is parallel to FD. Yeah, it's really interesting how this is similar to the last problem. Like I didn't try to do that at all. It was two completely different competitions. And so once we know that, this means that KL is perpendicular to OM. All right, so Anmol, what, so I think, so your proof used symmedians and harmonic quadrilaterals, it looks like, right? So MA is the symmedian in triangle MBC. Okay. So MA, MB, MC, let it intersect the circle of Y. Whoops. Yes, we know Pbqc is cyclic. Yeah, cyclic, yeah, and harmonic, yeah. So it's harmonic. There we go. Project onto AD. Okay. Project through M onto AD. I guess that's probably what you mean. So D, oh, onto AQ. Okay. So then we have A, P, Q, G is harmonic. And once we know APQG is harmonic, yes, we have to show that LK is parallel to DF. We compute AL over LK, or AL over AK, I'm guessing you mean. And I'm guessing maybe you're using that this cross ratio is 1. So yeah, AL over AQ is AK over AP. And then you're also using that this cross ratio is 1. And then I think you also use the angle bisector theorem, right? And then that would solve it when you combine all the ratios. That's pretty cool. So yeah, mine all cancel out, and then you have a different way and they all cancel out. I like it. I'm not going to type it up, but yeah, I think we understand it. Yeah. All right, sounds good. This one looks kind of hard. It's still from Black Mop. Let's see. This one's kind of interesting. Yeah, you guys can choose. So here's a problem on isogonal conjugates. Here is, this looks like an easier isosceles triangle problem, although I'm not sure it's that easy. And this one